Okay, good morning. This is our class on crystal growth in supercooled liquids, supercooled glass-forming liquids. We have seen the early stages of the phase transformation that glasses undergo when they are heated, that is crystallization. In the first stages we have nucleation and then crystal growth. The combination of both is called crystallization or overall crystallization. So let's then take a deeper look at crystal growth. Just a brief outline. We're going to give you an introduction on the physics and chemistry of crystal growth. Then there are several growth models, and 3 growth models are widely used to describe the growth kinetics in supercooled liquids: normal or continuous growth, screw dislocation growth, and the 2D surface nucleation growth. It's a mechanism that depends on a secondary type of nucleation. We are going to see in details in a minute. And then I'm going to give you some example of experimental results of growth rates in supercooled liquids and glasses, and how well these 3 models can describe these growth rates. Right. So, crystal growth rates normally depend basically on 3 factors. The undercooling or supercooling, how far the material you are interested is cooled down below the melting point or the liquidus temperature. Melting point for an stoichiometric system, liquids for a multi-component non-stoichiometric system where the chemical composition of the crystals is different from the chemical composition of the parent glass. The side factor, this is a very important factor, depending on how uniform is the crystal glass or crystal supercooled liquid interface is, a different mechanisms control the growth velocity. So the site factor is the number of available atomic sites where atoms can attach to the surface of a growing crystal. And of course, the diffusivity. As for crystal nucleation, in crystal growth, we have to deal with the diffusion coefficients of atoms or molecules in the liquid. They have to travel a little bit to attach to the surface of the growing crystal. One very interesting feature of crystal growth is that this is a spontaneous process. For crystal nucleation, one has, or the atoms, or the system has to overcome a thermodynamic barrier. There is, if you recall my previous lectures, W star is the thermodynamic barrier for nucleation. Fluctuations form and decay in a heated system if they are below a certain critical size. Only fluctuations above a certain critical size can grow. And there is W from work, there is a minimum work of formation of a critical size nucleus. So this is a thermodynamic barrier. Fluctuations form and decay, form and decay, form and decay unless they reach a certain critical size, which is system and temperature dependent, and then the system can evolve and they can grow. But crystal growth is spontaneous. There is no thermodynamic barrier. Once a critical nucleus is formed, it grows. The free energy of the system decays continuously. If you recall, the main plot for nucleation is something like this. So this is W as a function of the size of the fluctuation. So here we have W star. So fluctuations below W star or below this critical size, they dissolve back. But these fluctuations here grow. They come this way, they grow, the size increases, and the overall free energy drops. So this is a spontaneous process. This is what I'm talking about. Spontaneous process of growth. So nucleation growth, they are interconnected. They're really interconnected. No. Once they reach critical size, they start to grow spontaneously. So the diffusion coefficient here, the diffusion coefficient is likely to be very similar for both processes. Diffusion coefficient. It's not necessarily the same, but likely very, very similar, of the same order of magnitude, very similar temperature dependent for nucleation and growth. But this side factor does not appear in any equation of nucleation, but it does appear in equations for growth, because I'm going to show you why it does. And the undercooling, of course, appears in both nucleation and growth, because if you recall, delta G, the difference in free energy between the supercooled liquid and the crystal, depends on delta T, the undercooling. Excuse me. The undercooling is proportional to the difference between the melting point of the crystal and the actual temperature where we are studying the system. All right. Why is this relevant? Well, crystallization kinetics, the overall combination of nucleation and growth, allows or not the existence of the vitreous state. If you want to make a glass, you have to avoid crystallization. And also, if you are interested in developing new glass ceramics or improving the properties or microstructures of existing glass ceramics, it's very, very important to be able to control not only the nucleation kinetics, but also the crystal growth kinetics. So it has at least two main reasons for the importance of studying and understanding and controlling crystal growth kinetics. So let's take a look at the theory. How crystals grow? Well, there's a very famous painting by an Italian artist called Paolo Masacci. this painting is interesting because if you think of the surface of a growing crystal, it's not always perfect, you know. Think of these blocks as structural unities. So you may have one here, then there's a lacking structure here, then another one here, a hole there, and then another one. So think of these building blocks which are finding their ways and attaching themselves to the surface of a growing crystal. And that's the idea behind the 3 different growth models that I'm going to talk to you. Before we move into the theory, how people measure growth rates? Well, you normally find a crystal, you heat treat your sample, you make a good glass, then you heat treat it properly, find a crystal in a microscope, and follow the size evolution of that one crystal as a function of time. If you have a heating stage microscope, you can heat in the microscope, pick one crystal, any crystal, and follow how its size increases with time. If you don't have a heating stage microscope, you can also heat treat a sample for, say, 1 hour, quench the glass, and that's a nice feature of glasses. They're so viscous that they're good model systems to work and to understand crystal nucleation, crystal growth features. You heat treat the glass, and you quench that sample. Then you look at the crystal at room temperature. Then you can reheat that same sample for another hour or so. That crystal will grow, and then you quench it again, bring to the microscope and measure the size, and so on and so on, so you can follow the size evolution of a particular crystal. In this case, is a sodium disilicate glass, at 780 degrees Celsius in 1 minute intervals. And then you have a plot of size versus time for that particular temperature. The slope is the crystal growth rate. So you come here and you have one data point in this plot. This is now growth rate U. Some people call it U, other people call it V, but it's a growth rate in meters per second. Meters per second, temperature, one data point, one temperature. You move to another temperature, repeat all that procedure, have another data point, and then another data point, another, and so on. So by changing the temperature of study, you can have such wide variation of crystal growth rates, in this particular case, from 10 to the power minus 9 to 10 to the power minus 6. So 3 orders, 3 orders of magnitude of variation. Of course, coming towards the melting point, the growth rate is 0. So there is a range here where it's impossible to measure because it's so slow that it takes a long time to measure. And for other systems, the growth rates can be so high at the maximum that it's also not possible to measure. So it depends on the system. For this particular sodium disilicate supercooled liquid, it was possible to measure in a wide range of temperature, from a little bit below the melting point towards the glass transition temperature or so. So if you want to see a macroscopic view of nucleation growth, what we normally have is a wide variation of these two rates. So we normally plot here the log of the rate or the velocity as a function of the temperature. If this is the liquidus, the nucleation rate and the growth rate will be 0 at liquidus. And then the growth rate will reach a maximum and will decay. This is growth rates. And we have already seen that the homogeneous nucleation rates are normally peaked here close to close to the TG of the glass. And they become 0 here. So this is nucleation, homogeneous nucleation, and growth rates. The maximum growth rate for at least oxide glass forming liquids is about at 0.95 of the T liquidus. So this temperature here is about 0.95 of the liquidus in Kelvin. If you plot everything in Kelvin, this is 0.95, whereas the maximum nucleation rate is somewhere between 0.5 and 0.6 of the liquidus temperature. So this is the overall macro view of nucleation growth. All right. So as I said, for some systems, this maximum here can be measured. For other systems, it's so low, or when it's so low you cannot measure it at all. When it's so high, it's also outside the range of our experimental techniques, and we measure growth rates somewhere here and somewhere here, and then we have to try to see which model best fits the experimental data. And this will be your exercise for next week. You are going to take your adopted glass system, find out published data for crystal growth rates, and try to see which of the 3 models that I'm going to explain in a minute will fit your experimental data. This will be your next package of homework. Okay. So that's the kind of fit that you're going to do. You know, we have done here for this particular system is the experimental data, and you take 3 models and fit to see which one best describes your data. Sometimes none of these models will describe your data points, but let's see. In this particular case here, the fit is not very good. I mean, it describes reasonably well the temperature dependence in the magnitudes, but not perfectly. In any case, the fittings, you see that the fittings with crystal growth models are much, much, much better than the fittings with the nucleation model. If you recall, the nucleation model allows you to fit the temperature dependence, but not the magnitudes, unless you force fit with a temperature dependent sigma. But you have not done this for your homework, right? You have used a constant value of sigma. But here, the models work much better, luckily. Okay, so let's see the three classical mechanisms. In the so-called normal or continuous, you can write down in your notebooks, normal or continuous growth, and this has been observed for pure silica and pure GeO2 glass, for instance. People have tested these models and they found that these two systems have their growth rates very well described by this normal growth model. The normal growth model is very interesting. As I said, let's assume that each of these cubes represent a structural unity. Could be an SiO4 tetrahedron, for instance. Each unity is represented by a block. In the normal model, the interface, this is a growing crystal, the interface is rough in atomic scale. What I mean by rough is that there are atoms or unities here and holes here. There's a unit here and a holes here, a unit here, no unit here. So it's rough on an atomic scale. If we had a powerful microscope, electron microscope, looking at this interface, it would be rough. Half of the sites would be taken, and the other half would be empty. By empty, I mean available to capture some molecules or structural unities from the liquid to the crystal. In summary, for a rough interface, you have a lot of available sites for capture. That's the idea. And there are materials that behave like that. And for this case, the crystal growth model is very simple, as I'm going to show you. But before we move into the equations, there's another mechanism. The screw dislocation model, second mechanism, screw dislocation growth model, which is observed by sodium disilicate glass, sodium borate glass, diopside, and many glasses. This is the most common crystal growth mechanism. You have a very perfect interface with screw dislocations. If you recall from your material science classes, you remember what a screw dislocation is. Many crystals, or most crystals, have screw dislocations. So if they do have screw dislocations, atoms from the liquid prefer to attach here in the edges of these screw dislocations because they have higher energies than in the flat surface. So atoms come from here and attach here, from here, attach here, attach here, attach here, along the screw dislocations. So this is the most common model. And also, there's a third interesting model. If the growing crystal has a perfect interface, perfect, atoms from the liquid have a hard time to attach to that growing surface. So they have to nucleate again. That's called the two-dimensional or secondary surface nucleation growth model. This is like heterogeneous nucleation, but it's not heterogeneous because it's a secondary nucleation on a primary formed crystal. You have formed the crystal by primary nucleation, then this crystal can no longer grow because the interface is perfect. So there's a secondary nucleation, and then this secondary crystal grows, then there is another nucleation event and it grows and so on. So perfect there's a nucleus, secondary nucleus formed here. It grows, and then there is another one formed here, and then that's how the crystal grows. So it grows by secondary two-dimensional nucleation. This mechanism is not very common, but it has been observed a lot for polymers, for instance. Several polymers, their crystal growth rates are described well by this mechanism. In the oxide glass world, we have observed this particular mechanism for lead metasilicate and anorthite glass, for instance. They best describe the crystal growth. Anyway, these are the three major models. There are other models. And before I forget, I'm talking about crystal growth in stoichiometric systems. There's no variation of composition. For this simpler system, for instance, lead metasilicate glass, the crystal phase which grows as lead metasilicate crystal, and so on. We are talking about stoichiometric systems. When the composition of the crystal phase is widely different from the composition of the glass, then long-range diffusion has to occur, and then you have depleted layers, you have more complicated situations which can be dealt with, but I'm not going to tackle on those problems today in this class. Okay? Yes?
It's not possible to have two or more mechanisms in the same system, right? It's one of them.
It's possible. It's possible to have one mechanism in a certain temperature range and then a change of mechanism for other temperature range. Yes, it's possible. We have seen, at least in cordierite glass, I have worked with cordierite glass, and apparently it changes from a 2D mechanism to a screw dislocation mechanism. Yeah. So that's the secondary nucleus I was talking about. So let's now take a look at normal or continuous growth. So let's then take a look at the equations that describe this particular normal or continuous growth model. The idea is very, very simple. This is a famous plot, I believe was proposed by Svante Arrhenius many, many years ago. Arrhenius was a Nobel Prize winner of chemistry. And he came up with this idea of activated processes, you know, activation energy. You have heard of activation energy. And then very nice way to describe crystal growth is by using this plot of free energy versus position. Then you have a set of atoms in the liquid, L of liquid, and then if they move to a crystalline arrangement, you know, and this is a jump distance lambda, which is maybe 1, 2, 3 angstrom. This is the same lambda that we have seen in the nucleation theory. It's a jump distance. So the atoms are somewhere arranged in the liquid. Now they are in a crystal. And this is the concept of an activation energy for diffusion, delta G D of diffusion. They have to, even if they're already in the crystal in the crystal liquid interface, they have to rearrange themselves. So there is an activation energy to move, to break their bonds in the liquid and attach to the crystal. This is the delta GD. So there is a probability of coming from this position to this position. So you can write the probability of going from the liquid to the crystal is proportional to the vibration frequency and the exponential of minus delta GD over KT. However, not many people realize that there is also a probability of certain molecules here coming back to that position. It's a smaller probability, but it's non-zero. They are fluctuating and somebody's not so happy, you know, and they go back to the liquid state. So now the probability to go back from here to here has to overcome this delta G barrier. This is the free energy difference between the crystal and the liquid, plus that one. So now we have to do the probability of going back from the crystal to the liquid. It's proportional to the vibration frequency. The vibration frequency is of the order of 10 to the power 13 hertz or so. The atoms are vibrating, and the more they vibrate, the higher the probability of jumping. And now it's exp of minus delta GD plus delta G, this delta G here, in modulus. I'm putting this in modulus here because this is a negative quantity. So to avoid confusion, I use the modulus because the free energy of the crystal is always smaller than the free energy of the liquid. So it's best to use modulus to avoid confusion. So the net growth rate is just lambda, the jump distance, versus this delta probability, this minus this. This is the growth rate versus. So if you do all this difference, you'll find out that U is lambda, the vibration frequency. Oh, it's just to use the same notation, I'm writing down nu 0, vibration frequency, exp, the minus delta GD of RT, 1 minus exp, the minus delta G of RT. Well, you know that you can use R or K, you know. When you use KT, this is the Boltzmann constant. R is the gas constant. So they are related. They are related. When you are using in molar quantities, like the joules per mole, then the constant is the gas constant. When you use joules per molecule, then the Boltzmann constant. You know that they are related. What's the relationship between the two? Please remind me, what's the relationship between the Boltzmann constant and the gas constant? It's the Avogadro number. Avogadro number. So So R is the Boltzmann constant, let me think a little bit, divided by the Avogadro number, right? You have to remember of this relationship when you're doing your calculations. Please check to see if this is correct. You're checking. You have, it's okay? It's okay. You have to you know, be aware of these relationships because sometimes it's, people use R, other people use K, so you have to be really aware of this distinction because the relationship is 10 to the power 23 or so. So the errors is huge if you confuse one with the other. Anyway, this is a very simple equation. Very simple. It came from this easy derivation, and it says that the growth rate is a function of the temperature, is a function of the activation energy for diffusion and the free energy difference between the glass or the supercooled liquid and the crystal. So we only need these two parameters here to calculate the K is equal R over N. Yes. K is equal R over N. That's right. K, the Boltzmann constant, is equal R over Avogadro's number. Yes, right, because this is 10 to the minus 23, this is 10 to the plus 23, so, and R is only about 4, so yes, this is the correct expression. Thank you. This is interesting enough, remember this is for the normal growth. Because the normal growth, the interface, the crystal liquid interface is rough. Any atom from the liquid easily can be attached to the crystal interface. So the F, there is a F here, fraction of sites, the fraction of sites is about 1.5, 0.8 is negligible compared to these two exponential dependencies here. That's the beauty of this continuous or normal growth model. This is the final equation. For the screw dislocation, growth model, for the screw dislocation growth model, the only difference is that we can use F, which is proportional to the delta T over Tm. So the F now depends on the temperature. Remember that delta T is Tm minus T. So the fraction of sites now depends on the temperature. There is a factor F, a multiplying factor F, which is temperature dependent, and this is normally smaller than 1 for screw dislocation. For normal growth, F is close to 1. And constant does not depend on the temperature. Here, for screw dislocation, F depends on temperature. These are very simple equations. What's the major problem with this equation here? Now that you have seen all the theory about nucleation, which parameter here we normally do not know? The diffusion. This delta GD here, this diffusion part, we don't know. If we are dealing with a very complex oxide glass forming system, we don't know. Is it the diffusion of silicon, of oxygen, of some molecule? We don't know. Delta G is okay. You have already learned how to calculate or to measure delta G, the free energy difference. If you know the specific heats of the supercooled liquid, the specific heat of the crystal, and the heat of melting, this we can calculate or find in a table or even measure in a calorimeter. But this is complicated. So here we are going to do the same kind of approximation that we have done for crystal nucleation. What was the approximation that we have used for crystal nucleation? The Stokes-Einstein iron equation. So the Stokes-Einstein iron equation indicates that the coefficient of diffusion controlling viscosity is proportional to the Boltzmann constant times the temperature divided by lambda, our jump distance, this lambda here, and the viscosity. So we have somehow to replace this part here by the Stokes-Einstein equation, right? Okay then, we are faced with a problem now that this quantity here is unknown. To escape from this problem, which is not a problem of the crystal growth model, it's our problem, that people are going to use the crystal growth model to understand or to get some insights in their crystal growth experiments. For the interpretation of their crystal growth experiments, we make an extra assumption that the Stokes-Einstein iron equation, which is d eta equals to the Boltzmann constant times the absolute temperature divided by lambda times the viscosity, can be used to describe growth rate. The assumption we are making here is that whatever mechanisms are controlling the diffusion processes in viscous flow are the same that control the diffusion processes in crystal growth. So the unities of this diffusion coefficient is meters squared per second. And the unities of the term we are interested, this term here, lambda is 0 esp of minus delta GD over RT, the unit of this is meter per second. So to replace all this part in the equation by dN, we have to divide the n by lambda square, because now the unit here will be meter per second. So our final expression for U will be U as a function of temperature will be equal to kT over lambda square eta times 1 minus S minus delta GD over RT. And here we multiply by F, where F is given by this expression here for the screw dislocation mechanism, and is negligible, around 1.8 or so for the normal growth mechanism. So now we are in business. This is the equation that you guys and ladies are going to use for your homework. You're going to try to fit experimental data to your adopted glass using this equation here. And for such a test, the controlling parameters that you need are the viscosity and delta G. Viscosity and delta G. You already have the viscosity and delta G because you have used these two parameters to test the classical nucleation theory. The only free parameter is lambda. You can leave lambda as an adjustable free parameter and see what happens. You have a good result if you're able to fit the temperature dependence of the growth rates and get a resulting value of lambda of about 1, 2, 3 angstroms, maybe 5 angstroms, not 1 kilometer. If it's 1 mile, 1 kilometer, you're off. It has to be a few angstroms. And the poor lambda, it's a poor lambda because all the errors, the experimental errors of your data, and the errors of the viscosity, and errors of here, there are errors. They all go to lambda because you're leaving lambda as your adjustable free parameter. So this poor constant will be blamed because all the errors will reflect in the value of lambda. But it cannot be 1 mile. It has to be a few angstroms. From half angstrom to 10, something like that, I'll be happy. Let's see. Let's see what happens. However, there is still a third mechanism. We have covered the normal growth, the screw dislocation growth, but there is now a third mechanism, which is more complicated because it relies on a secondary nucleation. So let's take a look at this third mechanism. Okay, just to finish with my transparencies, we have then the final form of the equation with an F here for normal growth. F is constant, and for the screw dislocation growth model, this is the final. You can compare this expression with our expression here. We are okay because there is a lambda here, but there is a lambda cube here, so they cancel out to give lambda square. So we did our homework. Okay, this is the expression for screw dislocation. And well, as I said, F is approximately the melting point minus T divided by Tm. This is a factor 2 pi here, but this is a constant, so it doesn't matter too much. Of course, this is the thermodynamic part, this is the diffusion part, and as I said, there is no free energy barrier here. The only barrier that we have for growth is the diffusion barrier. There is a diffusion barrier. This is no barrier. This is just the delta G, it's not W. This is just the thermodynamic driving force. These two terms, they fight with each other. If you remember, the more we undercool the system, the higher the delta G, the more willing to crystallize the system becomes. It wants to crystallize to decrease the overall free energy. But the diffusion part becomes more and more important. It becomes harder and harder and harder to diffuse. That's why there is a maximum. It's a maximum. It's the fight between the thermodynamic and the transport part. Now, let's take a look at the third mechanism, the secondary surface nucleation growth. This is more complicated, and I'm going to show you the final form of the equation because it will take a long time to derive this expression. The final form is the following. The growth rate is some constant, again divided by the viscosity, x the minus b over t delta g. I'm going to show you the value of b. The value of b, now we have, this is a free energy barrier because it depends on nucleation again. The value of b depends on two sub-mechanisms. There are two sub-mechanisms. The so-called small crystal case, where the size of the secondary nucleus is about the same size as the primary crystal, and large crystal case, when the primary crystal is this big and the size of the nucleus is this big. So the value of B here depends on whether you deal with the small crystal case or the large crystal case. For any of these two types or sub-cases, you see a similarity with the primary nucleation expression. If you take the final form, for the 2D secondary nucleation growth model, we are dealing with growth. It's 2D secondary nucleation controlling growth. The final form is something like that. U is equal to some constant T over eta exp the minus some constant 2 sigma square divided by T delta G. Again, what's the expression for primary nucleation? Just from last class, primary nucleation. The expression is I is some constant T over eta exp minus some constant dash sigma square T delta G square, right? This is what you have been working with. So what's the difference between these two expressions? Now sigma squared, secondary nucleation, here sigma cube. Another difference, delta G. Delta G is now 1, and here is 2. This is the difference in the key parameters. You know, the key parameters are always the viscosity, sigma, and delta G. These are the key parameters. All the other parameters are constant. So, your next homework then is to get your glass, find crystal growth data, and test the 3 or 4, I should say, because this is divided in 2 parts, but it's the same general equation. If, you know, one of these 3.5 mechanisms can describe the growth rates for your glass. And then you get lambda as an adjustable parameter. But in this case here, you don't know sigma. So you have to either leave sigma and lambda as an adjustable parameter, or just to make your lives easier, let's calculate lambda. For this case here, let's take lambda as the square root of the volume of the crystal phase. So you calculate this and leave only sigma as adjustable parameter for this particular case. For this case here, your adjustable parameter will be lambda. There is no sigma. Luckily, there is no sigma in this case. Okay? Is the whole story clear enough or not? Fala um pouquinho.
Can I ask in Portuguese?
Yes.
O lambda para aparecer na equação da secondary nucleation, ele vai aparecer dentro da constante, né?
Ele está aqui dentro. Ele está aqui dentro. I wrote in approximate form because there are 2 forms, so lambda is here in this C. She is asking, let me translate for our international guests. She is asking, where is lambda? Lambda has disappeared? No, lambda is inside the constant. I have only written a short form of the equation. Lambda is here.
So we need to put the C like one of these values because
the C you're going to calculate. You know the constant. In the blackboard, you see the whole value of the constant. You have to calculate the constant, leave only sigma as an adjustable free parameter, like you did for primary nucleation. What you're going to do here is to plot, here you plot this following graph here. You plot log of U times eta divided by T So U times eta divided by T versus 1 over T delta G. T delta G. And then if things work okay, you have a plot like this. And from the straight line, you get the value of sigma. If you get the straight line. For primary nucleation, you have plotted I times eta divided by T versus 1 over T delta G square. Now it's delta G, not square here. Delta G 1. This is the test that you can do to check whether the 2D secondary nucleation growth model describes your data.
O que significa o velho?
Volume molar. Molar, VM is the molar volume. S? NS is the number, NS is the number of sites on the surface of a crystal. So it's you remember that you have NV. You have calculated NV for your exercise with primary nucleation. This is similar, so it's NS. But you don't have to bother too much because you come here, the whole constant will be here. Your pre-exponential. This is your pre-exponential. The pre-exponential log C, you get it from the straight line. All these constants, all the multipliers, like you did for the primary nucleation. You get the pre-exponential here when you extrapolate this to 0, and the sigma from the slope. So you get the two parameters from this linear fit. So NS, lambda, everything will be included here. Okay?
And which value for sigma is like, okay?
Well, the typical values for sigma are like 100 millijoules per square meter or 150 millijoules per square meter. Millijoules is 100 millijoules, or like you get, let's say in ergs, like you got from normal values, there's 200 ergs per square centimeter, 100 ergs per square centimeter, something in this range, the same range that you got from your nucleation experiments. You got a value of sigma from your nucleation fitting exercise, somewhere in this range.
There is another difficulty here.
That lambda enters in B. See? Lambda enters here and enters here. So lambda is everywhere. It doesn't matter. You're going to calculate previously the value of lambda, taking the volume of the crystal lattice and calculating the cubic root of the volume of your crystal lattice. This will give it'll be a few angstroms for lambda. Let's see what happens with this exercise. But before I finish this class, what time is it now, please? 11:30. 11:30. Let me very briefly, in 5-10 minutes, show you then the results of all these exercises. Normal growth is d divided by lambda, which gives this lambda square here. Here we have a f, and here you have a whole different expression. You have a different expression which resembles the expression for primary nucleation. Of course, to test these models, you need the Gibbs free energy as a function of temperature for your system. You can either use one of the approximations, like the Hoffman expression, or the Turnbull expression, or experimental values, if you have them. So the same that you did for your previous homework. Of course, you need the viscosity, but you already have for your system. And then, well, this is just for fun, to show you one of my ex-students has measured a growth rate in situ for a particular glass diopside. You can see 2 crystals here, and then they grow after some time. See, 2 minutes, 1 minute, 2 minutes, they're this size, 2.5 minutes, they grew a little bit, 3 minutes, grew a little bit, grew a little bit, grew a little bit. So this is how he measured the growth rates of his crystals. Anyway, and this for a particular system, these are experimental data, and the fit with, in this particular case, the screw dislocation model. And the resulting lambda look very nice. 1.1 angstroms, very, very nice value. It came here not perfect. You see, there's not perfectly, because also different people have measured growth rates, and this is a complication because every glass is different from the other glass. Like I make a glass here, it will have certain impurities, it will have certain departures from stoichiometry. Like Maziar, you make a glass in Iran with your chemicals, with your different relative humidity, you have different impurities, you use a different crucible, different degrees of OH groups. So it's impossible to have data from different authors to agree completely. So I don't expect these fittings to be perfect, but this is good enough. I mean, I'm talking about 10, almost 10 to the power minus 11 to minus 4. I mean, this is 7 orders of magnitude. 7 orders of magnitude. It's a nice fit. One thing that I have to warn you, there is a breakdown here at about 1.1 of Tg. For, you cannot see in this graph, but for lower temperatures, the Stokes-Einstein equation can no longer be used. And this has been done for several systems, and the overall result is that there is a breakdown. This is well known in the literature. If you come here and plot like log of growth rates versus temperature, is a calculated curve with viscosity. This is calculated with viscosity, and the growth rates are okay, and then normally there is a breakdown at T breakdown, and this temperature of breakdown is around 1.1 to 1.2 above the TG of the glass. So here would be the TG of the glass. The curve calculated with viscosity can no longer describe because there is a breakdown. I'm telling you this because this is an important phenomenon and you have to use data above 1.1 of TG. If for your particular system there is data below, don't take those. Take data above 1.1, 1.15 of TG for your fitting. Otherwise you'll be messing about why it doesn't fit, but this is because of this breakdown of the SCE. So let me write this down. This is the breakdown. Breakdown of the SEE. Okay? Any questions? Right then, thank you very much. See you all next week for overall crystallization kinetics. Bye-bye.